Good afternoon, everyone, from my side. Namir unfortunately cannot be part of the webinar today, so I will be hosting and doing the Q&A session later on. So yeah, welcome to the second last TDS webinar for the year of our third series, which we have run successfully every month so far. It's a great initiative and it always attracts a good amount of people, so really pleased with that. Our webinars are sponsored by our sponsors. We have XLAM, Simpson Strong Tie, FutureBuild LVL, iBuild, Mytech, and Rotoblast. So thanks for their support for making it happen. And obviously we have the support in the background with Nicola from Engineering New Zealand. And always a big thank to Namir organizing these seminars every month. So today we have Ben Moerman connecting from Vancouver in Canada. He will talk about high-capacity shear walls, and he will talk about his research program he has carried out at the University of Canterbury. And looking forward to the next webinar on the 7th of December, where we have another webinar about shear walls, which is about light timber frame shear walls, and it's more about the basic principles of designing a very simple shear wall as such. As Nicola was saying, Ben will present, and then after the end, there will be a Q&A session. So pop in your questions as we go, and then I will facilitate that, and Ben will then provide answer. Right, so to the speaker of today. So Ben Moerman is a Canadian structural engineer who has a keen interest in seismic behavior of buildings in an innovative structural system. He completed his PhD at the University of Canterbury here in Christchurch. And that's where he researched the high-capacity CLT shear walls. He's now back at Structurecraft in Canada, and it's very great to have you with us today, Ben. And with this, I let you start. Thank you very much.
Great, thanks, Daniel. And yeah, thanks to the Timber Design Society for letting me share my research. I always hoped it would be something practical that could help push the industry forward, and sharing the work that's been done is one step to doing that. So thanks for having me, and thanks to everyone for attending. So my topic for my thesis is on high capacity CLT shear walls, and it was under the supervision of Ming-Hao Lee, and as well as the co-supervisors Alessandro Palermo, Tobias Smith, and Angela Liu. So off we go. Quick overview of what we're going to talk about today. First, just the need for high capacity CLT shear walls. Basically, why bother spending 3.5 years researching them? Second is talking about cantilever walls, some cyclic experiments using some high capacity connections. Then into coupled walls, where I'll talk about a few connection schemes that actually let us build a coupled wall system, as well as the design of those connections, the system, and cyclic testing. Then beyond just the connection testing, we'll go into how we tested the whole system, and then how we repaired it and retested it. Then following the experiments, we knew the system worked, so we did some analysis and proposed a seismic design method. And hopefully I can do it all in 30 or 40 minutes. Finally, I'll wrap it up with a few key conclusions. So to kick it off, why do we need high capacity CLT shear walls? So CLT has been around for quite a while. You can see a basic layup shown at the top there. And this is a mass timber product. It's glued up dimensional lumber, and what it basically is, and what I tell people, especially that aren't in the industry, it's just jumbo plywood. And since it's jumbo, we can make bigger connections. It's got a lot more in-plane strength and stiffness, and so it's really well suited to be a shear wall element, not just floor plates. Some of the first tests that were done on CLT shear walls looked kind of like this. So here at the base here, so I'll just turn on my laser pointer. We see an angle bracket here. It's just light gauge metal bent into an L shape and fastened with a lot of nails. And then at the hold downs, it's usually a longer strap to try to develop more uplift resistance. And yeah, this test was done by Gavrich. Similar tests have also been done by others. And then one of the most notable tests done to date was at the E-Defense table in Japan. This was the SOFI test done by Ario Cicciotti and his research partners. And basically what all these tests demonstrated is that ductile failure in the fasteners can be reliably achieved. And that's really what we want in earthquakes. We want something to bend and yield and absorb, turn that kinetic energy into hysteretic energy, and basically reduce how much our buildings are moving and deflecting. So this is kind of state of the art. This is what I call conventional CLT shear walls. Often they're platform framed, so similar to light timber, where you build your first story of walls, then you build your first story floor plate, and you carry on up the building. You can see here on the right, these are some typical connectors that you might see, like I showed in the other slide post-test. And so it's basically light gauge metal, it's nails, maybe ring shank nails, screws, that type of stuff. And the peak strength is typically going to be less than 100 kilonewton, especially at the design level. So really the main problem and the driver for this research was CLT has significantly greater in-plane strength and stiffness than plywood, but right now we're still using the same connections and framing scheme used in light timber frames. So in my opinion, the use of CLT shear walls, using these types of connections, we're not really fully utilizing the material in lateral strength and stiffness terms. So how do we solve that problem? The first solution is pretty intuitive. The connections are too weak, so let's use stronger connections. We can put some much more significant stress into the wood. On the left here is a test from Canterbury a couple of years before I got there by Lisa Ottenhaus, and she was looking at high capacity dowel connections. So this one, there's 16 dowels, and they were seeing peak strengths of about 1,000 kilonewtons. Another similar test that's really putting significant stress in CLT was done by Thomas Wright, and this was around the same time I was at Canterbury, and similar strength levels. He was getting up around 1,000 kilonewtons. So with these types of connections, then we're actually getting in the range of, we start getting worried about the failure of the timber, not just the fastener. So we got to be careful, but it's also the best way to get high utilization out of our material. The second solution to the problem of basically weak, soft CLT shear walls is alternative wall framing configurations. So instead of platform framing, we can balloon frame it. We can do either a single wall, or we can go all the way to a different type of configuration and do beam coupled walls, which I'll talk about later on. So that's basically the basis for why I wanted to investigate high capacity CLT shear walls. And now we'll get into some of the experiments. So first is just cantilever walls, and we wanted to do some cyclic tests. And basically those two connections I showed earlier with the dowels and the screws, we knew uniaxially we could get really high capacities out of the connections, but then we wanted to put it together into a wall system and push and pull on it and see how the walls behave. So we did 6 tests in this program. The first one was a long wall, then we did a roughly square wall. It's a little bit taller than a square, but and then the third one was a tall wall. So the aspect ratio is basically 0.5, 1.3, and around 3. Each specimen we did, or each geometry we did twice, once with each type of hold down, a bolted and then a screwed hold down. So this is the basic test setup. We've got these hydraulic actuators out of plane, and we didn't load the walls out of plane. These were strictly just for stability. They had nice spherical bearing connections on each side, so as the wall moved back and forth, they could laterally support the wall and not bind up while the wall was drifting back and forth. And then we had the hydraulic actuator here, which was actually pushing and pulling on the wall, and a big clamp to pass the force into it. The 2 types of hold downs we used that I mentioned earlier. So one was a mixed angle screw hold down, where you have a combination of 90 degree and 45 degree screws. And the reason we do that is that the incline screws at 45 degrees give really high stiffness, and the 90-degree screws give really good ductility. I'm not the first to use these hold downs, but we were the first to use these at the base of a cantilever wall, and really put some high forces into this. And then the other connection we looked at was just a bolted hold down. So it was 4 bolts, varying diameters depending on the test. And yeah, you can see the plate's a bit oversized. We wanted some flexibility to possibly add more bolts, but we just stuck with 4. The walls were tested with the Curie loading protocol. This was a protocol set up for light timber frame, but is also practically relevant for what we were doing with CLT. So we pushed and pulled on all the walls back and forth, and these are some of the results. You can see all these plots are severely pinched, where in reinforced concrete and steel, when it's well detailed, you'd see the curve look more like this, something more like elastoplastic. But in CLT, it responds hysteretically kind of similar to light timber frame, where we get lots of pinching, and that means less stiffness, less energy dissipation versus elastoplastic system. Yeah, on the x-axis here, we have global drift. On the y is actuator force or base moment for these. So you can kind of get a feel for what forces we were getting up to, sort of around 700-800 kilonewton in the long wall, 400 in the square wall, and about 200 in the tall wall. So some typical damage that we observed in the bolted hold downs, they were nice and slender, or slender enough, I should say. And we got 4 plastic hinges here. And you can see that basically the dowel started in a straight line up here. And as the wall uplifted, it slowly bent, it locally crushed this timber, and we got some nice hinging behavior in the dowel, or bolt, sorry. In the screwed hold down, we saw as the wall uplifted, the screws slowly pulled out and also bent. So you can see basically some good hinges in the 90-degree screws. In the incline screws, they basically just, yeah, pulled their way out. You can see them hanging there. And we also saw a little bit of toe crushing just at the ends of the walls. Nothing too dramatic. There's definitely been worse in other tests, such as post-tensioned timber walls. You can really get a lot of compression concentration there, but we still saw some damage in the fibers. This is a bit of a description of how each of the walls deformed, and there's a lot going on, so I'll just explain how this graph is set up before I try to draw any conclusions or highlight anything. So if we look at each cluster of 3 bars, this is one test specimen. And if we look at each bar within that cluster, basically the first bar represents at the point in the history of the test when it hit its yield force, and then its peak force, and then its ultimate force. And then each color within that bar, that's representing how much, basically, if we look at the displacement at the top of the wall, how much that displacement came from in-plane bending, in-plane shear, base sliding, and base rotation. So we can see a different breakdown. For example, in the long walls, these 2 specimens on the left here, we can see that 40% of the displacement came from rotation, another 40% or so came from base sliding, and a small amount from in-plane shear, almost 20%. And as we change the aspect ratio of the wall, we get drastically different things participating in the deformation of that wall. So for the taller walls, we're basically seeing no base sliding, and we're seeing quite a bit of in-plane bending. Another thing to note is as we go from yield to peak to ultimate force, we're getting less and less in-plane behavior because our ductile link is at the base. So as that goes inelastic, that becomes a bigger and bigger portion of our wall's deformation. A key observation from this is that in-plane deformations can be significant. We can't just simply treat CLT as being a rigid body, which is really convenient for design. And if we're using low capacity connectors, it may be valid. But as we push the utilization up, the in-plane deformations, they play a significant role. Comparing some of the walls we tested to conventional CLT's walls tested to date, Basically on the left here is a table of several studies that tested CLT shear walls with these conventional connectors, so light gauge metal and lots of nails or light gauge screws. And really the important thing to look at here is looking at what sort of peak lateral force we have here. And yeah, if you go into my thesis or we have a journal publication in the Journal of Structural Engineering, there's a bit more detail to dig into. But one thing that we wanted to really look at is what's our strength utilization here. And what that is basically like how, based on the connections that were used, how close did we actually get to hitting the nominal strength of the CLT fibers. And yeah, previous tests, they were quite low, sort of maybe around 20-25%. Some were a bit higher, but what we wanted to do is push that right up to 100%, and that's getting a much more efficient design. We can compare two of the walls from the ones that we tested at Canterbury with similar aspect ratios, because most of the heights were sort of between 2 and 3 meters of previous tests. And what we can see is the max lateral force was basically 190 kilonewtons versus 540 in our tests. And the stiffness was also a bit greater in our tests. And you can see here our strength utilizations. We were, particularly in the latter 4 tests, we were pushing up around 100% or even over for some of them. So I think generally speaking, we can say from these cantilever wall tests, we can get really high capacities out of these CLT shear walls. And that opens up all sorts of new opportunities for using them in buildings. Now on to coupled walls. So we'll first focus on the connections, and then we'll zoom out and look at the overall system test. Before we go to the connection, just want to describe how the system's working. I'm sure there's probably several people on this call that have either designed or learned about designing reinforced concrete coupled walls. And really the system principles are exactly the same here. We have 2 walls that are paired together with link beams or coupling beams. And if we zoom in on that one beam, we see each wall is deflecting over. It's putting our link beams in double curvature. And the only way to actually impose that, impose those forces in that displaced shape on the link beam is if we have a good enough connection, because we're counting on that steel link beam to yield and dissipate energy in our system. And if that force can't be transferred over that joint, then the system's not going to work as intended. So this connection, generally speaking, we can say it needs to be stiff enough. So we're actually engaging and putting that beam into bending. It's also got to be strong enough, so we avoid connection damage before that link beam reaches its peak strength. And this is basic capacity design. So after lots of hand calcs and picking people's brains and a bit of finite element modeling, we basically narrowed it down to 3 connections that we thought would work. And we were kind of hedging our bets because we wanted to do our coupled wall test, but first we needed to establish a good connection to do those tests. So we came up with 3, we tested them all, and then picked the best one to use in the system test. The first one on the left here is just using an internal knife plate and lots of self-drilling dowels. The second one's using a bolted end plate, so really stealing from the steel world, because these bolted end plates are quite convenient in moment frames. And then we have a little cutout in the CLT, and the end of our bolt just receives a washer and nut there. And then we have our self-tapping screws to form a screwed end plate. So a bit of an adaptation over here, using long fully threaded screws from the timber world. And really a key thing that I'll show in the next slide here is basically a bit of grout just in this joint here. And I'll explain the reason for that. The first test we did were on this dowel group. So we did 3 tests with ductile link beams. We were pretty confident in calculating the connection capacity, so this was really a proof of concept. Then for the bolted end plate connection, we did 6 tests with a strong beam. So intentionally we wanted to fail the timber because we weren't sure what the actual failure mode would be. And when you're doing capacity design of a coupled wall system, you really got to know your the capacity of the brittle elements, which in this case is the timber. And finally, for the same reason, we did 14 tests of the screwed end plate connection with a strong beam. So we were forcing connection failure so we could really understand that connection capacity. And then one final test with a ductile beam. This is the test setup. So we flipped the system 90 degrees and split it at the middle of the link beam, which would be an inflection point. We had some guides at the top here just to keep everything stable. And then we were pushing and pulling right here. So the ductile group, the dowel group first, we saw, it was really successful, no connection damage and no significant connection damage. A small amount of fracture just in the wide flange there. And when we split the specimen open, there's a little bit of local crushing just at the holes of the dowels, and but otherwise no real damage to speak of. We got a nice ductile hysteresis loop, lots of energy dissipation, which was great. And we can just see a little loss of stiffness as we cross the axes there. And as best I can tell, the reason for that is because we got a little bit of local crushing here. So just every time that dowel's load direction changes, it just has to move through a little bit of free space where it crushed the timber. And that's enough to see a little bit of stiffness loss, but not too bad. Then looking at the bolted end plate. So we got a really interesting failure here. And these kind of failures in CLT in the in-plane direction are, I think there's still a pretty good research gap in that area. And so this was a pretty cool failure to see. You can see it split all the way there and pulled left and right, fracturing the timber. Also a little bit of a failure there. And then this is a cut looking down, and you can see it's fractured all through the CLT panel. This can be explained with a little strut and tie diagram here. So we have our bearing here, our moment's cranking over. We have compression there, so it's strutting out, creating a tie up at the top and the bottom here. And then this was the ultimate failure point. The force displacement plots are not too interesting because it was mainly just linear elastic and then it broke. So really the important thing here was the failure load, and then we could go away and figure out some design methods so that failure doesn't happen in a overall coupled wall system. This was the final test in the bolted end plate series. So we did a ductile link beam, and we can see our grout here perform really nice. And I realize I forgot to explain why we have the grout there, so I'll do that now. Basically, this system is really sensitive to getting that connection dead tight, and to get proper tolerance in the steel and in the timber, it would just be too cost prohibitive. And I'm not even convinced every fabricator could hit, fraction of a millimeter tolerance. It's just not practical. And so what we did is we oversized that joint by 10 millimeters and then just poured some base plate grout in there. We waterproofed the timber so it wasn't leaching out water from the grout. But that way we could guarantee a tight connection, and then in the overall system, we're engaging those link beams right away. But overall in this test, the grout looked really good. Just tiny hairline cracks. And so this test was a success. Moving over to the screwed end plate connection, really all we saw was screw failures. So we were getting a fracture right in there. We can see the countersunk screws in the steel end plate there. Fracturing, the grout looked pretty good. All this damage is just from taking the specimen apart, and you can see the fractured off screw heads. A little bit of yielding in the gusset plate, but nothing too bad. And then finally, the last one of the screwed end plates, we also did a ductile beam and capacity design the connection. So we got a nice ductile failure. You can see yielding in the flanges and a nice hysteresis curve here. So onto the system test. We finished out the connection testing, decided that the screwed end plate was the best one of the set. and decided to use it in the system. So yeah, this is the general test setup. You can see, yeah, I'll just step through each part of the test setup, but hopefully you have a good idea of how it works. So the lateral load is applied on the right side here. We have 3 link beams, and they're stiffened just like active steel links in eccentric brace frames. We've got hold downs at the bottom. We've got shear keys to keep the walls from sliding. And then on the left side here, we've got collector beams. So the force comes into this channel. There's 2 pins right in the middle of the wall. I think they were 70 millimeters in diameter. And then those transferred their load onto drag plates, and then the load was in the CLT pier. We've also got out-of-plane supports, so those were just to keep things stable. Again, we weren't loading things in the out-of-plane direction. I got a video here. I apologize in advance for the poor frame rate over Zoom, but yeah, it's too cool of a test not to show. So yeah, pushing and pulling, getting a little bit of dissipation. And yeah, if you watch the link beams, you can see that we're really concentrating damage in there. So you're getting lots of yielding now. And this next one is just a zoomed in view of the link beam. Yeah. So you can see mill scale flaking off the webs of this beam. So that's showing that the web's yielding. And then you can see the flanges start to yield and inelastically buckle. And yeah, maybe I'll just play that one more time. It was a little bit quick. There's a publication on this testing that's been accepted, and it should be out any day now in the Journal of Structural Engineering. And once that's out, I'll share it on LinkedIn, and there's some YouTube videos. All this stuff is going to be on YouTube. So yeah, well, we'll focus in on the beam after. We'll first look at the wall base and look at some typical damage that we saw throughout the test. So in the hold down, basically we saw some local crushing around the screws as they were bending, and the incline screws were pulling out. So yeah, you can see they're pretty significantly withdrawn. I think at this part of the wall, we were seeing uplifts of 150 millimeters or so. You can see those screws are withdrawn and bent. In the link beam, like I said, there was local flange buckling. We had mill scale flaking due to yielding, and overall the connection was okay. So yeah, the connection scheme worked out. The capacity design was all right, and yeah, overall I'd say like this test demonstrated that this form of lateral load resisting system is very feasible, and yeah, we're getting quite high capacities. So for reference, this wall overall was about just under 5 meters long, and we got a peak force of about 600 kilonewtons, and that happened at 2% drift. So overall, I feel, you know, the system was reasonably stiff. It's usually something timber systems struggle with is just stiffness, especially at the SLS level. And in this coupled wall system, we have the link beams tying the piers together, stiffening everything up, and yeah, overall performed reasonably well. We can yeah, we can see we did get some pinching, some just like the cantilever walls, but it wasn't as severe, and especially if you you know, ignore that last cycle all the way to ultimate, the pinching wasn't too severe. Following the test, we wanted to repair it, not only to yeah, get another test out of this whole setup, but also to see that in the real world, if we had a damaged building with this system, does it have a hope of being repaired? So we pulled out the screws and took out the grout between the steel beam and the wall, pulled all the beams out of there, and then we installed new link beams. So yeah, those black pieces of plywood there, we just forming it up, and then we pumped some grout into that joint and installed new screws. There was also damage at the toe of the wall, so we had a couple boards delaminate, which we reattached, basically trading what used to be an adhesive connection for a mechanical connection just with inclined screws. And then where the screwed hold downs were damaged, following a method that Thomas Wright came up with, we could basically take out the screws, drill out the loose fiber, fill in some epoxy, and then just fasten the screws, I think it was about 20 or 25 millimeters over from where we repaired the holes. And then we had a new hold down ready for the next test. Yeah, I won't show you the video because it looks very similar to the last one, but this is the hysteresis curve of each test. And you can see, so W41, W41 was the original test and 41R was the repaired test. So you can see that, you know, very, very similar behavior. We had a tiny bit more strength in the repaired test, but overall, you know, performed really well. I want to caveat this repaired test with, you know, saying this is not really a low damage system. There's been a lot of money and manpower spent on studying low damage systems, and in my opinion, I wouldn't quite qualify this as being low damage or functional recovery. You know, I don't think this system fits within that paradigm. What I will say is this system has a reasonable chance of economical repair after a design level earthquake, which makes me sound a bit like a lawyer, but you know, I see this system as having a hope of repair, which maybe is you know, a happy medium between not considering any kind of repair and base isolating everything. And yeah, caveat it with you know, it's repairable if the diaphragm is okay, if the residual drifts aren't too bad, if the damaged components can be accessed. Like we saw in the you know, the aftermath of the Christchurch earthquakes, there's obviously a lot of factors to repairing buildings and you know, what's actually economically feasible. So we saw that the coupled wall system worked, and we're happy with the concept. We had some experimental data to calibrate models. So then we wanted to put on our designer hats and figure out how to analyze them in a reasonably simple way and how we could design them for new buildings. What we proposed is a force-based design method, so you can allocate the component strengths with a final nonlinear analysis. So this is an iterative force-based design, and yeah, it's not the most simple design method out there, but I do feel that it's necessary for this system. And that's the great thing about doing academic research is we're not confined by, you know, we don't have to come up with the simplest method. We have to come up with the right method where the system can be designed well. And in my opinion, this was the best way to do that. So the basic steps in this, so we're going to assume a force reduction factor, and then we're going to check it. So we assume our factor, we design our ductile elements, basically just following the same procedure they use for reinforced concrete coupled walls. Then we're going to do some capacity design on the CLT wall piers. We'll check our hold down capacity and that local block tear out or crushing isn't going to govern us. Then we'll go create a nonlinear model. And that can either be one capable just of a pushover or a cyclic test, or a cyclic protocol. So either we're going to simulate ground motions with it, or we're just going to push it over and observe the performance. I think both methods can be worthwhile, and yeah, maybe it's a point of contention during the design process for the designer and the peer reviewer to work out. Before we actually went all the way and looked at a bunch of buildings and tried the design method, we wanted to get a bit of a feel for actually how the system behaves laterally. So following just the first couple steps of that design method on my last slide, we proportioned I don't know how many this is, 20 or 25 buildings, and ran pushovers for all of them. So yeah, a range of different stories from 4 up to 14 stories, some different link beams, different wall pier lengths. And yeah, we were basically comfortable that, you know, these systems are proportioned reasonably well and should perform okay. So we did a bunch of pushovers based on a open seas model that was calibrated to our experimental tests. So yeah, used the experimental data, came up with this open seas model, compared the two, did a bit of refinement, and found, yeah, this system works pretty good. So we can use it to simulate buildings. From each of those prototypes that we proportioned, we basically got a graph like this. And so what we could see is basically this is increasing drift level because, like I said, we were pushing it over. So the amount of base shear we can see for this particular system, which was a 9-story building, we hit our yield at about 0.3% drift. Then we hit peak at 0.8%, and then down to ultimate at 2% drift. We can also see like when the link beam started yielding, we can see, you know, the first hold down yielded here and the last hold down yielded here. And so it gave us a good feel for what's happening in the system. Because really, you know, this is a brand new type of lateral load resisting system. It's definitely similar to eccentric brace frames and reinforced concrete coupled walls. So there's some concepts that transfer, but just being timber and having discrete connections, and you know, there's so much variation in the type of link beam you choose and the hold down you choose. We felt we really needed to do these pushovers so you can actually feel what's going on in the system and how it's going to want to behave. So yeah, we did pushovers on all those buildings and pulled out a few key results that we could use to inform the subsequent designs. So one thing we can generally say is, you know, looking at the geometry of wall pier length to link beam length on the y-axis here, and global drift at yield and peak strength, we can see that our shear links, which are the orange dots, were just a lot better. They have a lot better drift capacity, and we hit yield at a lower drift level, which is already known. I think you know, shear controlled failures for eccentric brace frames is well known that that's a preferred mechanism. It is harder to achieve given architectural constraints, but yeah, that's a known fact. So similar for this system. Another thing that we saw was there's a lot of variability in displacement ductility, and that's why I think we need a force-based iterative approach for the design of these systems. There's just too much variation in how much displacement ductility the system has. Some other results that really are needed to inform the design of the system. One is the degree of coupling factor. So this is basically shown right here with this equation. And yeah, this is a common, well understood factor for concrete coupled wall systems. And what this says is basically, if we have an overturning moment for the whole system, what portion of that goes to the link beams and what portion of that goes to the moment at the base of each pier. And so we pushed it over, and we pushed all the systems over. You can see each black whisker here is basically one specimen or one prototype. And what we can see is basically a range of beta between 0.4 and 0.6 seems pretty reasonable. For all these systems that we proportioned, we didn't have any idea what beta factor they would have. Just proportion things based on capacity design, and that's sort of the range where they came out. So that seems about right for design. And what we also saw was basically there's a division of moments at the base of the piers between your tension pier and your compression pier. And so you can see this ratio change through the drift of the building. And yeah, at peak strength, this was sort of around 0.9. The compression pier is just stealing a lot of that base moment. So we felt we had a good understanding of how the system behaved, and went off and did some prototype building. So picked a rough layout, assumed a seismic weight for the floor plate that was reasonable for timber buildings, and looked at a 6, 8, and a 10-story building, just using the design procedure we proposed and seeing how it came out. So yeah, we for 6, 8, and the 10-story building, we used a 7-ply wall. For the hold downs, we had 12mm screws, a total of about 60 of them, and yeah, 6, 8, and 10 stories. Assumed a ductility factor of 4, and that's what we were going to try and verify after the fact. picked our ground motions, scaled them, and used our open seas model from earlier that was calibrated. So this is kind of what the results showed. First, just looking at the mean levels. Sorry, I'm just gonna have a drink. First looking at the mean interstory drift levels. So this is the 6, the 8, and the 10-story building. All of them showed a mean peak drift of around 1.5 to 1.6%, which isn't too bad for drift. So I felt the stiffnesses were reasonably good. And that sort of reinforced my thinking behind the design approach being a force-based approach. So we start with the forces, get everything, make sure it's strong enough, and then check the stiffness that it's okay. You can see in the 6-story building, one of the buildings was quite close to the 2.5% drift limit, and one of the models actually did show collapse from one of the ground motions. But yeah, if you compare basically the black line being the mean and the gray lines being every single model, you can see there's quite a bit of spread between the responses of different ground motions on the system. So I'll just summarize a few key conclusions and then we can move to Q&A. So first, we can say that mixed angle screw or bolted hold downs, they let us reach really significantly greater lateral capacities compared to conventional systems. These high capacity connections can be used to better utilize the in-plane capacity of CLT. As if we're using them for shear walls, we want to use them efficiently. Conclusion 2 is that all 3 of the beam to wall connections that we had schemed up showed adequate strength and stiffness, and they all were capable of providing capacity-based or capacity-protected connections. We'll say the screwed end plate connection seemed like the best one. There was some, these two require a higher degree of fabrication and tighter tolerances, whereas the screwed end plate connection is just very forgiving. Conclusion 3 is the hybrid coupled CLT shear wall configuration is a feasible lateral load resisting system with a very ductile failure mode. And if it's designed properly, then the damage will mainly concentrate in the link beams, as well as the hold downs and a bit in the compression toe. Conclusion 4 is it may be feasible to economically repair a coupled wall system after an earthquake. As I discussed, there's a few caveats with that. And conclusion 5, the proposed force-based design method can be used to reasonably proportion your component strengths. And if anyone's designing a system like this, I sure hope people do someday. But if you are, nonlinear verification is strongly encouraged to just make sure that adequate performance is achieved. So that's the end of my presentation. I hope it was clear and that you enjoyed it. And I hope it could be of some practical use to the industry in the future. So thank you for listening, and thanks again to the TDS for having me. Thanks to my sponsors, the lab technicians, and supervisory team, because they were all part of this work. So I'll take any questions now. Thanks.
Thank you, Ben, for your great presentation and for the step-by-step slides talking us through the different steps of your research and also how to design it. Before we go to the questions, I forgot to mention before, and I want to do it now. For the next year, we obviously want to continue the TDS webinars. And if there's any topic you would like to learn more, or if there's any topic you actually want to speak and share your knowledge to the wider audience, please share this information with us, flick us an email. Nicola put some text into the chat box, so please get in touch. We are welcoming any sort of feedback. Right, Ben, back to your presentation. There's a few questions coming in. In one of the last slides, you talked about shear links performing better, and the graph showed flexural links. Can you tell us a little bit more about what you mean with the flexural links, and when you said the shear links function better or behave better compared to what?
Yep, yeah, that's fair. Basically for these steel link beams, I'm really stealing concepts from its eccentric brace frames in steel construction. And so when you have, if you think of a given steel link beam, if you make it really long, when it goes into bending, it's going to develop moment hinges at the end, kind of like a moment frame. And if it gets really short, you have a higher shear content compared to your moment demand. And so when the shear is very high, then you'll end up yielding in the web instead of the flanges. And based on lots of experiments other people have done, not just myself, that shear yielding is a lot more stable and it won't buckle at, or the flexural link beams will buckle a lot sooner for a given, for a given drift level. The shear length is going to be a lot more stable than a flexural link. And yeah, the shear links will buckle a lot later at a higher drift.
Thank you for that. There were a few questions about the, let's call it the stiffness of the link beams when connected to the timber. So I summarized them up. First of all, was there any thoughts on the long-term effects around that? So if the timber, essentially, if the timber comes in slightly wet and starts drying, there might be a gap. So is this tight fit of concern? And the second question is, you talk about grout, so we assume it's cementitious grout. Have you considered epoxy grout as an alternative? And wouldn't it be better, considering that cementitious grout would essentially wetten the timber around it, therefore swelling it and therefore creating a potential shrinkage problem later on?
Yep, no, those are good questions. I think a great thing about these keyed in connections is that they're in CLT. And so we have some fibers in both directions. And so as far as in plane shrinkage, it should be very, very minimal, because we know in timber, most of the shrinkage and the swelling is perp to grain. So I don't see any need for major concern over the long-term behavior of that joint. Yeah, in the thickness direction, it may shrink and expand, but I don't think it's significant. To the point of epoxy versus cementitious grout, yeah, I just went for cementitious grout as a first attempt because it's cheap and it's everywhere, and we know we can mix it up and make it very flowable, and it'll fill everywhere. And yeah, in terms of causing swelling in the timber, like we painted the timber interface that the grout was going to touch, and so yeah, the timber didn't soak up any of that moisture, and because that would compromise the grout and try to swell the timber. So yeah, the cementitious grout worked okay. I didn't have any issues with it, and we didn't see any problems. But yeah, epoxy grout could work for sure. It just reduces the, or sorry, it increases the cost of the system, and we're just trying to be efficient.
Thank you. It's good to know there's alternatives as well if someone wanted to. One attendee is asking, so your testing video seems to show that you push the specimen to failure or to really high drift levels. What kind of damage have you observed during a typical SLS and ULS design event?
Yeah, that's a good question. It was pretty tough to see any damage until we got up to, I want to say something like 1% or something like that. Then you could actually, I'm talking like if you didn't have the graph to look at on the controller in the test, like you could just start seeing some of the screws were starting to come slack from the damage. And then around, I think around 1% drift or a little bit higher, then you could see the mill scale flaking on the steel beams. So you could recognize damage there. But yeah, the damage was pretty minimal until we hit sort of around 2% drift. And then there was actually notable damage. But SLS levels looked pretty good. And when we did the connection tests, we cycled probably 50, 60 times just at very low load levels because we wanted to see if the grout just turns to sand after lots of cycles. And yeah, we didn't see any issues there.
Thank you. And there's a lot of questions coming, so I keep going a bit and you tell me when it's getting too much.
No, feel free. Yeah.
So you made a comment about the low damage or the non-low damage behavior of the system currently. There's a question, do you think you could achieve a more low damage system by introducing other low damage joint technologies like the resilient slip friction joints? Like, do you think there is a potential to extend the link beam somehow?
Yeah, I think so. I think what goes between the wall piers is quite flexible. I don't mean that in stiffness terms. I mean, you can swap in different components there. Yeah, if it's a proprietary device or some sort of viscous damper to help control like wind SLS in non-seismic zones, I think there's lots of options to put in there. There's also the option of post-tensioning the wall piers down. So there's definitely variations off of this system that are possible. We wanted to take a first step and try stay within the realm of, the steel link beams are well understood. And so we used those between the wall piers and we knew the base connections would work. So we were trying to put together a system that had a good hope of working. But there's definitely room for variation. And yeah, it's really getting that shear and moment connection right. And I think we have some solutions for it. And so what component goes between is up to the imagination of the engineer.
Correct. And I guess that almost would create a second PhD out of your research. So we leave that to someone else later on.
Yes.
That's another more generic one. But do you think that your coupled wall system could replace EBF steel frames in certain applications, certain buildings?
I think so. I think EBFs, they're still going to be they're going to have a better performance overall than timber because to really put big drifts on the steel link beams, it seemed to me like the base of the pier needed to lift up. And once you get damage in that hold down, it creates some pinching. And so I think steel EBFs will always perform a little bit better. And they're also going to always have a lot higher capacity because what I found was limiting was you can really only put in a certain size link beam in there. And once you get too deep, then the demands on the CLT is just too high. And it's, you can maybe go up to a 9-ply CLT, but there's a point where it just starts getting uneconomical. And so, yeah, my general feeling is it could maybe replace EBFs in certain buildings, maybe up to, 8 or 10 stories, something like that. And beyond that, it might be more challenging and just not worth the effort.
Mm-hmm. Thanks for that. But yeah, really good feedback, Ben. Thank you. Another question, more specific again. Did you calculate the toe compression deflection and the area over which this is happening? And if you did, could you match the results with your model?
Yeah, we did. Like in the paper, we do have some plots of neutral axis depth. So we know our compression block length, but yeah, as far as how much toe compression actually happened, could probably be back calculated. I can't remember off the top of my head. I think it was the compression block was maybe 10-20% of the pier length or something like that.
Mm-hmm. Right, we probably leave that to the paper if someone can look it up, and once available, you said you post it on LinkedIn, so thanks for that.
Yep.
So a few more questions. Did you find a significant different shear and curvature demand on the links up the height of the building, or were they more or less used and deformed the same way? Yeah,
they were pretty uniform. I'd have to double check. I'm pretty sure the top link beams tended to yield first. I'm talking in the analytical model. And you can sort of think of that as the ones at the base, they sort of see whatever sort of imposed drifts that the base is going to put on it. And then as you go up the wall, the in-plane deformations grow. And so, yeah, the upper link beams closest to the roof tended to yield first. But in the experiment, it was a scaled down system. So it was 3 stories scaled at 2/3. And the CLT walls are generally pretty stiff in plane. And so, yeah, the shear and moment was pretty uniform over the 3 of those. But as you go taller, then you would see a bit more difference.
Thank you for that. Another question about, do you think that any introduction of gravity loads into the piers would have a significant effect on the lateral behavior?
Yeah, no, that's a good point. And I still don't know if it's the best idea whether or not to put the gravity load on the coupled wall, or if you want to kind of decouple the two. But yeah, I think the main concern would be then just concentration of compression force at the toe, because you'd have that combined effect of the gravity plus the overturning moment trying to crush that portion of the system. So yeah, it would be significant. It's got to be checked in the modeling and the design.
Okay, a few more. You showed your link connection. You showed 3 different ones. I think one was bolted or doweled, one was with a backing plate and rods in tension, and the third one was with fully threaded screws in withdrawal. There's a question, have you considered using epoxide fixings like epoxide rod instead? Or would that be because obviously that's a much more brittle mechanism if it goes. Would you consider that? And I'm adding to this question, what overstrength have you considered or would you recommend using?
Yeah, so the epoxy rods, in hindsight, I kind of wish we looked at them, but you can't do everything. And yeah, I kind of tried to stay away from epoxy because I know some engineers are a bit hesitant to even use it because it just comes with quality control headaches and different stuff. So I tried to stay away from it if we could. It doesn't mean you have to. I think epoxy rods are a really good option and probably better than the bolted end plate connection we tested. So yeah, definitely could be used. And yeah, as far as the overstrength for the link beams, I was just pulling from the New Zealand steel code and just looking at the eccentric brace frames and using the overstrength factors there. It seemed to work out, and it was pretty accurate for both the component tests and the system tests that we did. But yeah, like you said, for epoxied rods, you might want to build in a little extra conservatism there, because they're quite brittle failure, and so are the actually loaded screws. They're quite brittle as well. So definitely doesn't hurt to keep your utilization a little low on those connections.
Yeah, I would agree with you because you don't want to lose that specific connection out of the whole system. Mm-hmm. Right, let's go to the last one. A really good question, so thanks for everyone adding to this. So you mentioned residual drifts might preclude reuse of the building following a significant earthquake. Did your research attempt to estimate the residual drift or qualify whether it will have an impact on the uptake of the system in practice?
Yeah, it's a good question. No, I didn't look at estimating the residual drifts. I think they would broadly be similar to whatever's seen in eccentric brace frames because the mechanism is generally similar. But yeah, it's a serious issue with a lot of systems. It's a lot of reinforced concrete and steel systems too. They'll have residual drifts. The one thing in this system is, you can always take your steel link beams out and then just push the piers back straight, and that would fix your residual drift issues. That being said, if the building's drifting so much you can't even get people inside safely to access it, then that's a different issue. So yeah, the repairability is, I think there's potential, but it's just very situational. So I don't want to overpromise.
Thank you, Ben, for all your answers and the insight. There's probably more questions, but maybe flick Ben a message on LinkedIn or see what this paper can provide with more information. I think we leave it at this. It's 1 p.m. for us. I think it's 4 p.m. for you, almost home time. Ben, thank you so much for taking the time and sharing all this information with us here today and for contributing to the way we build mass timber. So thanks very much, and thanks everyone for listening in, and looking forward to the next webinar on the 7th of December. Right, thanks everyone, and goodbye.
Thank you.